going to talk about related rates. Related rates are still dealing with derivatives as rates of change, but now what we're going to be looking at is two or more variables that themselves change with respect to time. Here are two such problems that we would be using related rates to solve. An oil leak spreads in a circular patch with the radius increasing at a known rate. How fast is the area of the oil patch changing? Or I could have two planes approaching each other, each at known speeds. How fast is the distance between those two planes changing? Let's look at the first question. If I give you that the radius of the oil patch is increasing at a rate of 30 meters per hour, and I ask how fast is the area of the patch increasing when the radius is 100 meters, this is how I'd set it up. First of all, I know the following. I know that the derivative with respect to time of the radius is 30. I could either write this as dr dt or r prime. So now I need to come up with an equation for the area of this oil patch. Since I know this is going in a circular patch, the area of a circle is pi r squared. So this is my area. If I now want to find the derivative of a with respect to time, I'll take the derivative of both sides. So the derivative of a with respect to t is simply a prime, and on the right hand side I'm using implicit differentiation because again r is a function of t, so the derivative would be 2 times pi times r to the 2 minus 1 power, or r, times the derivative of r prime, times the derivative of r. Well, luckily I know what r prime is equal to. That's simply equal to 30. So I can say that a prime as a function of t is simply equal to whatever the current radius is times 2 pi times 30, or 60 pi r. The question is asking what happens when r is equal to 100, and I simply plug in 100 for r, and when I plug that in I simply get 6,000 pi meters squared per hour. So the rate of change depends on what radius value I'm at a particular time. As the radius of the circle gets larger, the rate of change also gets larger, which makes sense because the area is equal to that radius squared. So now let's take the example of two planes approaching each other. Let's say one plane is flying west at 120 miles per hour and one is flying due north at 150 miles an hour. Both are flying at the same elevation towards the same airport. How fast is the rate of change of distance between the planes changing when the first plane is 180 miles from the airport and the second is 225 miles from the airport? In red, I'm writing what the basic steps are for solving related rates problems. The first one is to read the problem carefully and to make a sketch and identify what rates of change you're given and what rates of change you need to determine. So let's draw this. So I'm going to have the plane flying west be plane A, and the distance from the airport as a function of time is a of t. Plane B will be the plane flying north, and its distance from the airport is given as bt. I'm given the rate of change of A and the rate of change of B. A prime is 120 and B prime is 150. That's how fast those planes are traveling. So I've made a sketch, I've identified the rates given, and I'm still looking for the rate to be determined. Well, that's going to be the distance between these two planes, and I'm going to call this d. So d is going to be the distance between plane A and B, and that changes as a function of time. So once I have this identified, my next step is the following. The next step is to write one or more equations expressing the relationship between the variables. I'm going to quickly go back to my first example. That was when I identified that the area equals pi times r squared. For this example, looking at my sketch, it looks like this is a right triangle, so I think the relationship I'm going to use is that dt squared is equal to a squared plus b squared. That's using Pythagorean theorem. The third step is just to differentiate with respect to time. We're going to be usually using implicit differentiation for this. So if I take this equation and take the derivative with respect to time of both sides, using the chain rule, I get that 2d times d prime is equal to 2a times a prime plus 2b times b prime. I want to solve for d prime, when recognizing that I can factor 2 out of the numerator and denominator. I get the following. So now, step 4, I simply substitute in my known quantities and solve. So in this case, d prime is equal to a times, so in this case, d prime is equal to a times a prime, which was given as 120, plus b times b prime, which was given as 150, divided by d. And this question specifically asked what happens when a is 180 miles away and b is 225 miles away. I know everything but d. To solve for d, I simply am going to use the Pythagorean theorem, where d is equal to 180 squared plus 225 squared, and that's going to be approximately equal to 288. I'll use that in my denominator, and then I end up with a distance equaling 192 miles per hour. My very last step is to check units and see if my answer is reasonable. And if I look at this, the rate of change, or the change of the distance between my planes, is 192. 192. What bothers me is that seems like the more time that goes by, the greater the distance will be between my planes. Really, as time goes by, that distance should be getting smaller and smaller. So I think I've made a sign error. I think when I made this assumption that a was equal to 120, that really wasn't correct. That rate of change is actually negative 120. And b is equal to negative 150. That is, as time goes by, I get closer and closer to the airport. My distance is decreasing. If that a prime was actually negative, when I go to this step, I'd have negative signs there and negative signs there, and I would end up with negative 192 miles an hour. So this is a very important last step because it's easy to make mistakes about positive or negative rates of change. You could have gotten a correct answer of 192 except for the sign. Let's do another example. We have an hourglass that's shaped like a cone. Sand is draining at the rate of 2.2 inches cubed per minute. If my hourglass is 5 inches tall and has a radius of 2 inches, how fast is the sand level dropping when the sand is at 3 inches deep? So again, let's go through our steps. We're first going to make a sketch and identify the rates that I'm given and the rates that I need to determine. So here's my sketch. I've got my hourglass. It's 5 inches tall and 2 inches at the top. As time goes by, the height of the sand is given by ht, and the radius at that time is given by r of t. What am I given? I'm given the change of volume as a function of t. That's equal to 2.25. So that means I've got to do a little bit of thinking on how I'm going to relate my h and my r to my rate that I'm given. And that's what I'm going to do in my second step. I know I want the rate of change of the height of the sand as a function of time. So that is, I need to find dh dt. So I think I can come up with a relationship between the volume and my height and my radius. The volume of a cone is given by 1/3 pi r squared times h. I know my final equation. I want to have that v prime and I want to have an h prime. It's the r that I'm not quite sure what to do with. So what I'm going to do is take my picture from above and recognize that I always am going to have a similar triangle set up. So if the shape of my overall cone, if that triangle formed by the radius and the height is 2 and 5, then the triangle formed by the level of the sand at a time t is that same similar triangle with sides length r and h. Therefore, 2 over 5 is going to be equal to 5 over h, and this is again by similar triangles. Therefore, I can rewrite my radius as 2h divided by 5. I'm going to plug that into my equation for the volume, and when I do that, I end up with my equation 4 pi over 75 times h cubed. Now I've got a single equation expressing the relationship between the things I want to find. Now I'm going to take that equation and take the derivative of both sides with respect to time. Once I have this, I can substitute in the values that I know. Once I do this, I can go ahead and solve for h prime But I'm actually jumping ahead and thinking about my last step. Is my answer going to be reasonable? The change of volume with respect to time being 2.25, that again, I don't think that's right. It's going to be negative 2.25 because the volume is getting smaller as a function of time. So I'll go back and make sure that's negative 2.25. So if I multiply this out and solve for h prime, I get that the rate of change of the height of the sand is approximately equal to negative 0.497 inches per minute. And that seems quite reasonable.